So I'm going to talk about a variety of things, and you'll see they're all basically related to each other. First, I want to either tell you or remind you how to properly think about quantum mechanics. Unfortunately, this way of thinking about quantum mechanics is still not standardly taught in undergraduate courses. And yet, anyway, thinking about it properly is a crucial zeroth order step to even talking about the cosmological questions. So let me remind you what you all learned in undergraduate courses. There's 3 axioms of quantum mechanics. One is if you have an observable O, then if it has observables or associated Hermitian operators, the eigenvectors have a definite value for the operator lambda. Okay? Right? Now, 2 is the probability postulate that if you happen not to be in one of these eigenstates and you measure O, if you're in the state psi and you measure O, then you get the value lambda with probability given by the overlap of psi and lambda mod squared. And 3 is the measurement or wave function collapse postulate. Well, so part A is that the wave function evolves unitarily in time according to some Hamiltonian until you make a measurement. And when you make a measurement, you collapse the wave function. In fact, if you start off with some state psi, after the measurement, you're in a density matrix rho given by the sum over the projection operators onto the eigenvalues of O weighted by the probability. Okay? So everyone happy with these things? You all remember this from kindergarten? Okay? Now, postulate 1 is perfectly fine. Postulates 2 and 3 are the ones that are sticky the second you start talking about things like the whole universe. Okay? That should be obvious. Fortunately, 2 and 3 are completely unnecessary. 2 and 3 actually follow from 1. So I want to tell you how to think about quantum mechanics with a unique wave function. One wave function. The words that go with the proper way of talking about these things, which you've probably heard, are words like decoherence and consistent histories. Oh, and I forgot to say, up here, again, when you're a little kid, they tell you that quantum mechanics is small and classical is large. This is also incorrect. The right words here are that quantum mechanics is a closed system and classical is an open system. Okay? So how many of you are fully versed in the ideas of decoherence, for example? Okay, I knew you would be. Okay. All right, then maybe I'll go a little slower. Okay. So, but remember, the ultimate goal is to remove these unneeded extra postulates and understand why they're not needed. So let me get rid of the third one first. The third one is the stupidest one of all, right? It's the one that everyone who first learns quantum mechanics hates. At least I did. Really? Little old me? When I make a measurement, I do this thing, then I collapse the wave function? What about my dog? Can the dog collapse a wave function? What about a little air molecule wandering by? Can the air molecule collapse a wave function? Okay. So it's totally unnecessary. There's no such thing as wave function collapse. All there is unitary evolution of the whole wave function. Okay, but the whole wave function is a wave function not only of the system that you're looking at, but also of any environment that it might couple to. And if you keep track of unitary evolution of this giant wave function, including the system and the environment, everything makes sense. You never have to invoke wave function collapse, and for every physical question you're interested in, you get the same answers, of course, as you get from this postulate. But we understand that these things arise because of interaction with a large environment or interaction with macroscopic detectors. And this is very important. Ultimately, quantum mechanics tells you, quantum mechanics does take away predictive power, right? We've known that for a long time. But you get patted on the head and say, oh, it's okay. You still get to make probabilistic predictions. It's okay. Okay? But those probabilistic predictions are associated with infinities. Infinite number of measurements involving infinitely large measurement apparatuses. Okay? And that's what I want to stress. And it's related, a completely related question, in fact, we'll see the isomorphic question, is why is it that the world looks classical? The world is really quantum mechanical. Why does it look classical? The naive answer is, well, you have little well-localized wave packets. Those behave classically. But that begs the question. How come we see states in the universe as little well-localized wave packets? Why, when I walk in the room, don't I see the TV there and a state 1 over root 2 there plus there? Okay? That's the real question, why is the world classical? Why don't we see states like that in nature? Why do we instead see approximately classical, well-localized states? Okay, so I want to answer that question first. Okay? So let's do it in the case of this chair, or whatever the hell it is, TV. Okay? So let's say that it was in a state AX1 plus BX2. And before I walked in the room, it was in this state. But there's other things in the room, right? There's like all the air molecules in the room, for example. Quite a lot of air molecules. 10 to the 30 air molecules in the room, give or take. But I don't know. So let's say that originally it's in this state and the air molecules are in some state. I'll call it initial air molecule. Oh God, I shouldn't call it that. I don't know. What did I call it here? Air initial. All right? Now something interesting happens though. Let me time evolve this state just a little bit, just for a little bit of time. What happens when I time evolve this state? Well, by linearity, so this is psi at t equals 0, right? Oh. Well, psi at t equals small is given by, well, by linearity, it's ax1, and then, now, what's going to happen? When you evolve in just a little bit of time, this thing isn't moving. But what's happened is some of the air molecules, which are whizzing around, have bounced off a bit, right? So the air molecules were going this way, now they're going that way. And the way they're going is correlated with where this guy was. Okay? So the new state of the air molecules, let's call the new state air correlated with the position x1. Okay? And, well, the other state is just plus b x2 air correlated with position x2. Now, a crucial fact is that those two states, air correlated with x1 and air correlated with x2, after an absolutely vanishing amount of time, minuscule amount of time, become very nearly orthogonal to each other. Okay? Air x1, air x2, at this time small, right? This is almost 0. Why is it almost 0? I mean, let's do something just totally extreme. So there's 10 to the 30 molecules. So let's say every one of the states, so there's 10 to the 30 states, right? So let's say air 1 for each one of the particles, and air 2 are only different by each other, I don't know, by 1%. Okay, so the overlap between air 1 and air 2 is 1%. Okay, well, then what is this overlap? It's 1%, but there's 10 to the 30 molecules. So it's 1% to the power of 10 to the 30. So it's because there's a huge number of degrees of freedom in the environment that in hardly any time at all. And the crucial thing is it has nothing to do with transferring energy, the air molecules moving this thing around. It's simply because there's lots of air molecules. And in enormous Hilbert spaces, it just takes tiny changes to make states orthogonal. Okay? Is that clear? So in general, this goes like some e to the minus some constant time n. And that's what matters. There's an n there. Okay? So that these things incredibly rapidly go to 0. Okay? Now that has a very important consequence. Let's say I want to compute any expectation value at all. Say I want to compute any expectation value involving the TV. Okay? Well, what do I do? So any expectation value for anything involving the TV is psi, the operator made out of TV variables, times psi. Okay? Well, but you see what happens here. This is equal to a mod squared x1 OTV x1 plus b mod squared x2 OTV x2. Now there are cross terms plus a star b x1 OTV x2 times the overlap between air 2 and air 1, if I'm doing it right, or the other way around, plus Hermitian conjugate. This is true at any time. At t equals 0, these states, air 1 and air 2, are the same. Okay? So I have a very entangled state. But in this vanishingly tiny time, these have gone effectively to 0. Okay? And what I'm left with is that any expectation value for TV operators is either with probability a mod squared, the TV is there, or with probability b mod squared, the TV is there. But it does not look like an entangled state. Okay? So quantum coherence is an incredibly delicate thing. Minuscule interactions with the environment are enough to kill it. Okay? This is why it's so hard to build a quantum computer. So this fact that when you interact, even with tiny coupling to enormous environments, you get is called decoherence. Okay? But you see, there's no need to invoke wave function collapse. There's just one big wave function that's evolving in a giant Hilbert space. But when I restrict to talking about the parts of it that I'm looking at, it behaves as if it's a mixed state. Okay? We can say that a little more formally. We can say that a little more formally by saying that originally I started off with a pure state. So there's a density matrix associated with that in the whole Hilbert space, which is just psi. But any expectation value for TV operators, or more generally, let's call them system operators, the system I'm looking at, is a trace of psi times O sub s. But because this doesn't depend on any environment variables, I can rewrite this as a trace first over the environment over psi, and then do the trace over the system times OS. And this sucker, the trace of the environment, the trace over the environment of psi is called the reduced density operator. So the statement is that if I look at the reduced density operator, if at t equals 0, the reduced density operator will look like a mod squared, b mod squared, a star b, and a b star for my x1, x2 basis. Okay? Then very, very rapidly, interaction with the environment evolves this to something that looks like a mod squared, b mod squared, 0, 0. With a 0 there means exponentially small in the number of degrees of freedom of the environment. Okay? So we don't need to separately invoke a wave function collapse hypothesis. It's just a part of the dynamics. And also, now, let's continue and talk about measurement. Well, I don't need to do anything different. It's exactly the same. Okay? Let's just use different letters. So let's say I'm doing a Stern-Gerlach experiment. Okay? Oh, by the way, I should say something. So this explains why position eigenstates are what we see. Rough position eigenstates are what we see as the classical states in nature. It's very satisfying. It should be the quantum theory that tells you what states look classical like. And it does tell you. It tells you that there is some preferred basis in which things decohere nicely. That basis is roughly a position eigenstate basis. Why? Because interactions are local. That's why. Okay. All right, so measurement is exactly the same thing. Let's say we start off with alpha up plus beta down. Okay? So I have a spin, but I also have some, I have my system, and I have a measuring apparatus A. And the whole Hamiltonian is some Hamiltonian for the system, for the apparatus, and some interaction Hamiltonian. Okay? So now what do? I feed this sucker in. So I start off, the apparatus is in its ground state. Okay? Okay? Now I time evolve this state. So if this is what psi of t equals 0 looks like, then again, psi of t is alpha up. Now, the whole point of this being a measurement is that someone, usually an experimentalist, has built the apparatus and dialed that interaction Hamiltonian in such a way that if you feed an up spin, the apparatus flashes up, I'm up. Okay? So there's some state of the apparatus. This is the whole point of this interaction Hamiltonian, is to evolve the state up ground into the state up, I'm flashing up. Okay? And beta down, I'm flashing down. But once again, for macroscopic apparatuses, the whole point is that these ups, downs, is effectively 0. It's e to the minus the number of degrees of freedom in the apparatus. Okay? And then isomorphic story to what we just went through. When you look at just system degrees of freedom, it looks like, after the measurement, with probability alpha mod squared, you saw up, probability beta mod squared, you saw down. Okay, so both the measurement problem and why things look classical are because quantum mechanics allows you to make predictions when you break the system up into two parts. One part which is huge. And in fact, really formally, for any finite apparatus or finite number of air molecules, we don't get exact answers. There's some tiny exponential e to the minus n degrees of freedom. So formally in our heads, we get perfectly sharp answers in an idealized limit where we make the apparatuses arbitrarily large, or in the case of environments, when the environment contains an infinite number of degrees of freedom. Okay? Happy? So whenever someone tells you that consciousness has something to do with the collapse of the wave function, what do you tell them?